Heather? I can't answer that. Okay. Okay, thanks again, everyone, for attending today's webinar, Why Choose Adhesives Over Traditional Fasteners, brought to you by Design World. Before we get started, just a couple of housekeeping details. If you wish to tweet about this webinar anytime during or after, you can use the hashtag #WhyAdhesives. This webinar will be available afterwards at designworldonline.com, and we will send it out to everyone who has registered. We will also have a Q&A session after the presentations, but you can go ahead and submit your questions, and we will ask them after the presenters are finished. So you can just use the GoToWebinar on your screen to put in your questions. We would like to thank our presenter, Brian Noonan, who is Global Technology Manager for Structural Adhesives for Hinkle Corporation, for being here today. A graduate of Northeastern University with a BS degree in Chemical Engineering and nearing completion of his Master's in Business Administration from the University of Connecticut, Brian is responsible for managing the product portfolio and new development strategy for structural adhesives. I'm Leslie Langnaw, Managing Editor for Design World, and I will be moderating this webinar today. So without much further ado, I'm going to hand over the mic to Brian.
Thank you, Leslie. First of all, I just wanted to thank everyone for taking the time out of their schedules to join us here today. I know many of you are joining us over your lunch break, and if your companies are like ours, we're all being asked to do more and more in the same amount of time, so I appreciate you guys joining us here for an hour or less to talk about why you would choose adhesives over traditional fasteners. So kind of the agenda here, talk a little bit about why you should listen to me when I talk to you, and why Loctite is an excellent partner for structural adhesives. Talk about just in general why you'd want to use adhesives versus mechanical fasteners. We'll talk about structural bonding economics, proper joint design, and then wrap up with some actual real-life examples. So why Brian? Leslie covered a couple things that I think are important. You know, I started my career here at Hinkle about 8 years ago in application engineering, and in doing that, I was working face-to-face with manufacturers and proving out the structural adhesives in real applications and helping get them up and running on their production lines. So I have some hands-on experience with these technologies at the manufacturing sites. I then spent 4 years in market development, which was focused on specialty vehicles. So a major part of that was structural bonding of sidewalls and floors and things like that. And in that role, I had to use what I had learned and help communicate that to others in the manufacturing world. And so I've got, you know, almost 10 years of experience directly related to structural adhesives. Why Loctite? Loctite, the brand, has been a trusted industry innovator since 1956 when Vernon Kriebel developed and patented the first anaerobic thread locker. And since then, we've been on the cutting edge of adhesives, innovating new products like light cure silicones and many things. So, you know, we're continuously on the leading edge there. And Hinkle is the largest adhesive company in the world. And you may have caught me say Hinkle earlier, and you see Loctite in the bottom corner. In 1998, Hinkle bought out Loctite, the company, and Loctite is now a brand within Hinkle, and Hinkle is truly the world's largest adhesive company. So, you know, you're hearing this advice from the biggest adhesive company in the world, who has continuously come out with the latest and greatest products. So, why bonding? I've probably had this conversation 100 times at trade shows. And when you look at these pictures, the question is, what do all three of these things have in common? And the answer is, all of them use adhesives in one way, shape, or form to make the final assembly. So, you know, when I run into someone at a trade show and they're trying to discuss with me, why would I want to use adhesives? You know, I've got this assembly, I've screwed it together today, I welded it together today, and it works fine. You know, how do I know adhesives are going to work? I don't trust it. and I ask them, how did you get here today? And many of them say, you know, I drove my car to the airport, I got on a plane, I flew here, I took a shuttle bus to the show, right? Well, the car you drove to the airport in is bonded together. The plane you flew here on is bonded together, and the shuttle bus you got to the show on are all glued together. So structural adhesives are being used in your day-to-day lives and all these other things. So it's not a question of can they work for your assembly, it's do they fit in with the economics and with the things you're trying to achieve to make your product better and more cost-effective. So, you know, we'll talk a little bit about why you'd want to use adhesives. The first one here is they join to similar substrates. The images you see here on the left-hand side is a boom truck, and that's bonding the fiberglass boom to a galvanized steel hub at the base of it. So you're bonding two dissimilar materials. On the right-hand side, maybe a slightly less aggressive application, but you've got a silver or stainless steel knife bonded to a glass handle. And the nice thing about adhesives, specifically an advantage over welds, is when you're welding, you have to have two of the same substrates. Adhesives allow you to bond to similar materials, which in many cases is a requirement. In addition to that, adhesives have a level of elasticity, and as parts heat up and cool, as you drive that boom truck from Alaska down to Georgia, there's differences in thermal expansion in the materials that are going to apply stresses to the joint, and adhesives are able to absorb that stress and not degrade over time. Adhesives also distribute stress evenly. On the right-hand side, you can see I've got two examples. One is of a bonded joint, and that's right here. And this would be two rectangular, in this case, steel lap shears that are bonded together on a 1 inch by 1 inch overlap. And on the right-hand side, you can see a bolted assembly. As you apply a shear stress to those assemblies, on the bonded assembly, the stress is distributed evenly along the entire bond area. So you can see this distribution of stress curve here showing you, slight peaks at the leading edges, but it's distributed over that entire area, as opposed to the bolted joint. And here you've got a concentration of stress not only at the leading edge, but also right where that bolt is. So if you tested these assemblies out to failure in an Instron or other mechanical properties device, many times you'd see the actual substrate fail, at many thousands of PSI with the adhesive assembly, and you're going to have a very distinct failure right at the bolt or spot weld with the bolted joints because they're not distributing that stress. We couldn't here today, but online there's a couple of videos that we've put together to show you the strength of bonds versus bolts, rivets, and spot welds. So you can actually go onto this website on the bottom, hinklena.com/Loctite Structurals, and you can view all these videos to show you the real-life testing of this distribution of stress. Adhesives fill large gaps. So if you're welding and you need to get these parts and tolerances really tight, that adds cost to the raw materials. The nice thing about adhesives is they can cure over varying gaps. So that may allow you to reduce the tolerances on your raw materials, which could help you cut costs. And it also, in this case, obviously they're potting the end of this hammer. And so it's actually filling up that spot and bonding that hammer head to the body itself. So adhesives can fill large gaps. They seal a joint also. Here's an example of one of our engineers doing a build at a trailer manufacturer, and they had screwed all these trailer floors in, and we were validating adhesive bonding of the floors. And one of the major benefits was when you screw into this floor, you're creating a leak path for moisture from the road to come up through and get into your trailer. So by bonding it, you're actually sealing it and bonding it in one step. So you eliminate that water ingress point, and you're also potentially reducing labor by cutting this down into a single step instead of two. You get a much neater appearance. Here's an example of, this is the side of a box truck, and on the left-hand side, you can see through bolts along the entire outside. And many of those through bolts are actually there to hold the E-track on the inside, and that E-track is a galvanized material, and it's what you use to tie down the cargo on the inside. And so on the right-hand side, we've eliminated those through bolts by using a structural adhesive to bond that E-track, and you can see the much smoother, neater appearance on the outside. So this helps this company differentiate their product in the marketplace and also command the premium for things like advertising space on the outside where it looks a lot nicer. and it's easily automated. So if you're talking about bolts and rivets, there's not a very easy way to automate those processes. If you're talking about welding, you can automate it, but you're probably talking about a significant capital investment. With adhesives, you can do anything from a manual application up to an integrated robotic cell like this, where you might have pick-and-place parts and have the whole thing controlled in an automated fashion, and at a much lower cost than automated welding. So the adhesives are easy to automate. So there you go. That's why you would choose adhesives, right? Well, I'm not going to completely ignore the considerations. It'd be easy for me to gloss over this part of the presentation, but I think it's important that we also talk about some of the reasons why you might not use adhesives, and then if you know these when you're doing your design, you can actually factor that into your thought process, and hopefully it makes it easier for you. So we'll spend a little bit of time on some of the considerations of adhesives. For one thing, they have to be cured. If you're welding or screwing or riveting, you just do it and it's done. Adhesives need to be cured, and that involves some type of process. So here on the top is a conveyor. Some adhesives are light cured, and you have to expend some money to buy this type of equipment and a process to get the part through there to cure it. And on the bottom, we're showing a two-part adhesive. So this is the two-part like an epoxy, where the parts are statically mixed through a mix nozzle and onto the part. So in some way, shape, or form, you're going to have to pick a curing method to make the adhesive cure on your part and give you the strength that you want. So that's one consideration. Kind of directly related to that is fixture time. All these adhesives are going to take a certain amount of time to fixture. In the case of light cure, it might be a matter of seconds. In the case of a two-part product, it's going to statically mix, and that might give you a matter of minutes for fixture time. But in either case, it's going to be some amount of time you have to let the product cure before you can pass it on in your assembly process. So that's really one of the major considerations and differentiations between mechanical fastening methods and adhesives is fixture time. Adhesives can be messy. If you knock over a box of bolts on your assembly floor, you can pick them up. It's real easy. If you talk about adhesives and you spill some on the floor, it's liquid, so you're going to have a mess. Now, there's clearly things you can do, like automating the assembly and making sure you have the right processes in place, but it is a consideration that adhesives can provide a messy work environment if not handled properly. And then to that point, proper handling. If it's the first adhesive you bring in your plant, or even the 50th, you're going to need to have the proper documentation in place and the proper training for your employees. So this is something that any adhesive supplier can provide you, but it is a consideration. You have to make sure that people know what they're using and are using it properly. And lastly is my favorite one. I gave you the example of the trade show where I'm talking to this person, and we're talking for 10 or 15 minutes of me trying to convince them that structural adhesives are going to work. It's going to be super strong, and it's going to last forever, and it's going to be great. And then once I finally convince them, you know what their next question is? How do I get it apart? And obviously there are certain times when that is important. If there's a certain part of an assembly you have to get to for warranty work or replacement parts, this could be a potential consideration, and there are ways to do it. Some elastomeric adhesives, like that your car windshield is bonded in with, you can use piano wire and you can cut it out with that. And even epoxies and acrylics, thermoset plastics, you can get those apart with heat. But it is a consideration that if you need to get it apart, you need to be picking a proper adhesive up front that's going to allow you to be able to do that. So those are the major benefits and considerations to why using an adhesive. And I probably could have done this all with one slide, because at the end of the day, from my experience working with different customers, you can spend all the time you want proving that adhesives are much, much stronger and all these different things. But really what it all comes down to is saving money. At the end of the day, switching to structural adhesives is going to have to put more dollars in your pocket if you're going to do it. And the three major ways that that's going to happen is either improve performance, they're going to distribute that load and give you a stronger final assembly, which is going to help you reduce scrap or warranty claims, and it's going to help you make more money. It's going to be a faster process. It's going to reduce secondary operations that have to do with welding or other things. That's going to increase your throughput, so you're going to be able to sell more of what you make, or it's going to help you decrease your labor cost. So at the end of the day, it all comes down, the economics all come down to one thing, is helping you save money. So when we're looking at other methods, I've kind of divided down to these three. You've got welding, you've got riveting, and fastening with nuts and bolts. And another thing I would throw in here too is like a double-sided adhesive tape, right? And the major differentiator here, like I've talked about, would be fixture time. When you're welding, you're riveting, you're fastening, or using double-sided tape, you've got instant fixture. And so these are that's a great thing to like in your manufacturing process. But there are some considerations. So I want to spend a little bit of time talking about, looking at these things side by side and the pros and the cons. So when you talk about welding, the major pro is very, very strong. And if you're doing an overlap weld on a part, that is the strongest thing you can do. We've done a lot of testing. I'll show you some data later in this presentation about lap shear strength. And if you spread our white paper, you've already seen it. But if you're doing overlap welding, that is the strongest thing you can do. There are some considerations with it. It's labor intensive. And I say that based on the fact that, yeah, it takes a lot of time to do a weld, but it's also costly labor. Welding labor is in high demand. It's a very specialized skill, and they make a good living at what they do. So it's expensive labor to do. In many cases, it distorts the substrate. So in some applications, this may not be a big deal, but on others, like at the stovetop we'll talk about later, there are actually secondary operations where people have to come back and grind the part, smooth it out, and those add cost and time to the operation. So that's something to consider. We already talked about you can't weld the similar metals, and then also galvanic corrosion can occur in welded joints. Mechanical fasteners, again, they're instant to develop your strength, and it's a well-known method. Between mechanical fasteners like rivets and screws and welds, this is what we were all taught in school. If you're a mechanical engineer, you spent a lot of your time learning how to design with these methods. And I know I went to school to be an engineer, and I never once learned about adhesives. So these are very comfortable methods to work with, and they provide you instant strength. Some considerations of mechanical fasteners. One, if you're using nuts and bolts, there's vibrational loosening. You've designed this assembly to work with that bolt tightened down to a certain tolerance, and the minute something leaves the shop, like a car or a trailer, if you don't do something, it probably vibrated loose, and it's now not operating the way you designed it. Now, being Loctite, we could certainly provide an alternative solution like thread lockers for that, but that's something to consider. These methods don't seal. Mechanical fasteners don't seal your part. So if you're worried about water or chemical exposure and you need to seal the part, you need to add a secondary sealing step if you're using mechanical fasteners in order to get that. Mechanical fasteners add weight. Some assemblies, it might not be a big deal, but in other things like trailers where there's hundreds or thousands of bolts and rivets that are in there, and the lighter you can make the vehicle, the more you can haul, the more your customers can make. That can be a differentiator. These processes are labor intensive. I'll show you a graph in a minute that kind of talks to, as you increase the area of what you're trying to assemble, mechanical fasteners and welds cost much, much more and take much more time than adhesives to put together. And mechanical fasteners are not aesthetically pleasing. We showed you that picture earlier. Talking to tape, this is a double-sided adhesive tapes here. Again, these provide instant fixture. So that's one of those major benefits. Some of the considerations are they are sensitive to contamination on the parts. The parts have to be very, very clean, and in some cases require a primer in order to get bond strength. So in many cases, if you factor in the amount of labor and time that went into prepping the parts and add that to your instant fixture, in quotes, the time that it would take an adhesive to fixture without those processes might be faster. The tapes are much lower in strength, which I'll show you in a minute, and they're also not adjustable. Once you press two parts together with double-sided tape, you've got your bond. So if you're working with big parts or parts where alignment is critical, that could be a major consideration for what you're doing. So here's a graph I've alluded to, and this shows you the shear strength along the y-axis versus alternative fastening methods. And for the adhesive on the far left and for the double-sided tape on the far right, I'm using a 1-inch overlapped joint to generate that shear stress. And as you can see, Loctite adhesives can give you up to 3,500 pounds force of strength on a 1-inch by 1-inch overlap. And then, the next one down, about half the strength is a spot weld. And the major differentiator there is that distribution of stress. If like I said, if you're welding that whole thing, that whole 1-inch area, it's stronger than an adhesive. But when you do just a spot weld, it's not as strong. And you can see the strength curve go all the way down to double-sided tapes on the bottom there. The dollar values you see there are the actual cost we've estimated it takes to assemble one of those parts. And some of the major assumptions we've taken here is one big driver in the difference in cost is skilled labor. You know, welding and some of these other processes take more skilled labor to do, so we're assuming a higher labor cost. And also we're assuming the same throughput. We talked a lot about how some of these methods take longer to do. So you know, we are saying it would take you longer to do some, and that's going to add more to the labor cost. But you know, this is basically what you're looking at. Adhesives are a very cost-effective solution, and they're providing you much, much more strength than a lot of these other alternatives. Here's a graph that is trying to speak to the strength over time, durability. That's another question I tend to get a lot. You know, hey, I see all your shear strength data you're creating in your lab, and it's all great, but how do I know it's going to last over time? And this graph was actually made in 1968, and I intentionally put that on there because you know, while it might be old data, it's real data, and it stands the test of time. You know, these were adhesives that were developed back then. And this is an S10 curve where you've got your maximum shear strength along the y-axis and the number of cycles to failure along the x-axis. And as you can see, the spot weld, the pop riveted, and the Loctite bonded joint. And you can see that the strongest assembly method, or the one that was the most durable and lasted the longest, was the adhesively assembled joint. And actually, this is on an aluminum lapped joint, and if I put the curve for the aluminum on here, it would only be slightly higher than that bonded joint. And the reason is, again, because you are distributing that stress across that entire load and not concentrating on those specific points that create weak spots over time as you cycle that load. So, you know, the durability of bonded joints withstands the test of time. Talking to the labor, this is the chart I referred to earlier. This is right from our white paper, which you can find on that same website, hinklena.com/Loctite structurals. And this is meant to show over varying areas on the x-axis how much time it'll take someone to put something together. So, you know, if you're putting together a 40-foot box truck, you know, that's a lot of area, a lot of linear feet you have to put rivets down or weld, let's say, in order to do it. Versus an adhesive assembly where you drop in a cartridge, you pull the trigger on your pneumatic gun, and you can draw a bead as fast as you can walk down the production line. So, you know, this is a graphical representation of the reduced labor costs you can get by going to a structural adhesive versus some of these alternative methods. So this kind of wraps up the cost portion of it, the cost-benefit analysis, and this is something that you know, I've done a million times, and you know, most of the time, if you can trust that it's going to work, if you can prove out to yourself that an adhesive is going to last over time, it's going to save you money. And you know, you can factor in some of those things we talked about as far as considerations and benefits, but once you get it to work, it's going to be a lower cost process for you. So, you know, the cost effectiveness is there. I want to spend a little bit of time talking about adhesive technology. And this right here is actually taken from the Loctite Adhesive Sourcebook. And on the top here, you can see a number of our different adhesive chemistries, from cyanoacrylates, which are superglues, epoxies, hot melts, all the way over to acrylics. And down the left-hand column, there are different attributes of the product: temperature resistance, adhesion, peel strength, etc. So, you know, this is here to really represent, hey, these are all the adhesive chemistries that are really out there. And when it comes down to it, there's really three major ones that we would consider structural. And that would be epoxies, two-part, and two-step acrylics. And these are the chemistries that, for the most part, are giving you 3,000 to 5,000 psi of shear strength on steel and stainless steel and aluminum. And these are the ones that are going to, you know, be a direct replacement for welds and rivets and give you that great ultimate strength. The only other thing I would add to this is that, depending on your application, some of these other chemistries can be structural adhesives. You know, depending on what the needs of your applications are, an elastomer or even a superglue might provide you with enough strength to be the only thing that's holding your part together. And that's really how I would describe a structural adhesive. It's what I'm relying on to structurally hold my part together. So while these three are the ones that you probably want to start with if you're trying something, any one of these can be a structural adhesive depending on what your application is. So, you know, I could have spent a lot of time talking about what makes those chemistries work and the chemistry behind them, but at the end of the day, you know, that's our job. That's the adhesive manufacturer's job to give you the right products to work for your assembly. you need to tell us what it is you're trying to do and what constraints you're working with. And so, if you're interested, we could certainly come out and give you a much more in-depth look at the chemistry, but that's all I'm going to cover today. The next thing I want to talk about briefly was joint design. And, this is probably a pretty basic review right here, but then I'm going to get into a little bit of what happens when you apply an adhesive force. So the four major types of forces you can put on a joint are tensile, compressive, shear, and peel or cleavage. And in these examples, the white here is a block of substrate, so it's like a metal, and this red is the adhesive. And that'll be consistent as we go through. So these are the four major designs you can have. And we'll talk a little bit about what happens. So if you're applying tensile strength, again, here, this white is the substrate, and this red is the adhesive, and these arrows represent the force you're applying. So if you're applying a tensile strength to that, across this entire bond area, which is blown up on top here, the stress is distributed completely evenly across the entire assembly. So this is an excellent force to design into your assembly in order to maximize the strength you can achieve with adhesives. Same thing with compression. Compression is actually even better. It's rare, you'll rarely ever see an adhesive fail in compression. So, when possible, these are things you want to try and maximize in your design in order to increase your effectiveness. Shear strength is probably the next one. This is a little different. Again, the white is the substrate, the red is the adhesive, but in this case, instead of applying a force vertically, we're pulling it side to side in shear. And as you can see, over that bond area, there's actually, the stress is distributed across the whole area, but there are peaks at the leading edge and at the trailing edge. So, this is the next most aggressive stress, let's say, because you've created those slight stress concentrations at the leading edge. But there's things you can do, like increasing the width of your bond line that the force is applied to in order to maximize the ultimate strength. And here's a little bit of why that happens. This is kind of an old graphic, not as nice as the other ones, but I think it really speaks to the point. In this case, this top set of rectangles here is the substrate. This one in the middle is the adhesive, and this one on the bottom is the substrate again. So as you apply that shear force, you can see the adhesive starts to move. And actually, if you look at this under very high-powered and close filming under an actual instron, or when you're mechanically testing it, you'll actually see this little bit of kind of substrate distortion happen, and that creates not a true distribution of stress. So, in a perfect world, if that little distortion didn't happen, you probably would have perfect distribution of stress. Because it does, you get that concentrating at the leading edges, and this is why. Lastly is a peel or cleavage force, and this is really where you're pulling up one side and holding the other constant. And the only difference between peel and cleavage is whether or not your substrates are rigid. If it's rigid, you have cleavage. If it's flexible, you have peel. And the takeaway here is you don't want these. These are the most aggressive forces you can put on an adhesive because you have concentrated all the stress on that leading edge of the joint. And when it starts to fail, it just keeps moving its way down the end. So you definitely want to try and avoid cleavage and peel in your design if you can. So there's ways to do it. I've provided you guys with a couple of pretty simple design alternatives for shear here, and again for peel here. And these are just different ways you can design out some of these considerations if you have them. And again, you'll get a copy of this presentation, so no need to furiously jot all this down. So in summary, for joint design, you want to maximize tension, compression, and shear. Those are the ones that are going to give you the most ultimate strength out of your assembly. You want to minimize your peel and cleavage. That's focusing the stress on one point, and you're losing that benefit of the adhesive to be able to distribute the stress evenly. And lastly, you want to increase your bond area. And remember, wider is better. Any way you can increase the bond area is going to help, but if you know the direction your stress is going to come from, if you can make that leading edge wider, it's going to give you a stronger ultimate assembly than if you make it longer. So those are the three major joint design guidelines when working with adhesives. So that's really all I had for joint design. And now I wanted to cover a couple of real-life examples. So, basically, up front we talked about why adhesives. Then we covered, some of the cost benefits and why they're going to save you money. We talked a little bit about joint design, and now this is really the, hey, here are the people who are actually doing this today. So this is meant to hopefully instill in you a little bit of confidence that, yeah, I'm not on the leading edge of this cusp. People have been doing this for years, which they have. And these are a couple specific examples that I've handpicked for us to talk about today. So the first one is the automotive impact test. And this is a test that one of the big three use to validate assembly methods specific to pillars, like your A-frame pillar and things like that. So in this assembly here, you can see it's two steel pieces that are actually riveted here 1 inch apart along the top and along the bottom. And on the far right-hand side, there's a fixture that's holding this in place. And on the left-hand side, there's a ram that's going to push up against it. And what they want to see is how this assembly is going to absorb the impact of this blow, and they want to see how it's going to fail. So if we look at the next slide here, this is not good. Basically, the rivets are popping out, so you're creating these, your assembly is no longer held together, and the failure mode is this very critical and acute bend of the part, so it's not really absorbing the stress. It's actually most of the stress is actually coming through into the back end of that, which is not what you want in a car crumple type of an application. So this was their riveted panel. The next one you're going to see is an adhesive bonded one. So again, same kind of application, except now these are actually bonded together with an epoxy. And it's a heavily modified epoxy with very, very good impact resistance. So again, you're going to see this stress applied with an impact from the left-hand side, and we'll show you what happens. In this case, the adhesive joint is still staying together. It hasn't failed, and what it's doing is it's crumpling. So this is what creates that crumpling in the front of a car. The adhesive is actually absorbing that load and folding in on itself, and that has to do with the properties of the adhesive being able to absorb that load and not concentrating in those rivets popping out. So this is one of the reasons why a lot of cars, almost pretty much every car, has a lot of adhesives in it, and it's because of this major benefit of the structural adhesives being able to absorb that impact load. So sticking kind of with the automotive example, but a little less abstract, here is a real-life application for Thomas Bus. And we have agreement with them to allow us to share this story because it's a good thing for them. They actually have the safest school bus on the road, and it's thanks to Hinkle Loctite structural adhesives. And these pictures right here are taken from an SAE case history that appeared in their magazine. And basically, they've eliminated the rivets that used to hold this assembly together, and are now using structural adhesive. And on the bottom, you can see it here. It's this gray product that's actually, it's hard to see because it's designed to match the frame itself. So squeeze out on the inside, it doesn't show up as dramatically. And the #1 driver, as pointed out, I'm talking about decision drivers, not bus drivers. The #1 driver to make the switch was improved safety. So you saw in that first example all those rivets popping free, right? Picture this school bus with a bunch of people inside. If there was an impact and the substrate ripped like it did with those rivets and they came loose, that creates a safety hazard on the inside of the bus. So by bonding it, when you have an impact on this thing, the actual joints stay together. The metal bends and folds, but it does not break free from where it is bonded together. So you have this initial, obviously, impact that's going to create something you don't want, but you're not going to compound that problem by having the substrate fail where these rivets are and these stresses are concentrated. So that's why this is, by the safety standards in North America, the safest bus out there. And if you look at the next school bus you see go by, you might see that it's glued together, and that's the main reason why. It also offers reductions in labor in the manufacturing process and improved longevity. You're not going to have rivets rusting out. You're not going to have part panels coming apart. The bus is going to survive longer out in the real-life opportunities or applications. The next thing is trailer bonding. So in this case, on the bottom here, you see a Loctite trailer. We actually built this trailer, partnered with a manufacturer in New York, and built this trailer all out of Loctite adhesive. So there's no screws or fasteners on this thing. It's all glued together with Loctite products. And in this market, while some people might consider their Harley-Davidsons or their ATVs their kids or their toys, and they might consider safety a big deal, the major driver for these guys is reduced labor cost. This is a highly cost-competitive market, And being able to draw an adhesive bead, like you see this gentleman in the top left-hand corner here doing, across that area in a fraction of the time it would have taken him to put in all the bolts and the screws and rivets that he would normally do, is the major reason why these guys have switched, many of them, to adhesives. That also allows them to have faster throughput, so when things are going well, they can crank out trailers much faster. And the improved aesthetics are a nice thing. Many end users like that smooth look, and especially people who are going to do advertising like we've done on the side here. It's much nicer to have that smooth side to work on than to have one with screws and rivets all down it. And the last example, I kind of noticed I had a lot of automotive type applications, so I went to something very different, which is stovetop bonding. And the application for structural adhesives is actually underneath that range top right there, which is the stainless steel. There's a bracket that they were welding on, which then allowed them to fasten that top to the rest of the assembly. And they were welding the bracket on, and one of their major, probably the biggest scrap issue they had in the plant was the fact that when they'd weld it, what you'd see on top was an imperfection. They would actually have to come back through and grind out that weld and smooth it out and make it more aesthetically pleasing for the end user. So the real driver to move to adhesives in this case was aesthetics. And when they didn't have the right aesthetics, they had to scrap the part. And that also, in this case, wasn't just due to the application of the welding and the grinding. These parts came in with a nice blue plastic sheeting on top. And if you could leave that on, if you bonded the parts and you could leave that on the exposed top area to a customer, the part could run through your whole plant and you're protecting it from anything else dinging it or scratching it as it goes along. But you had to peel that off in order to weld the spot. So it wasn't only an issue of the welding creating aesthetic issues, but it was also creating a process problem where once you peel that sheet off, you might somewhere down the line ding it, and then it became scrap, and stainless steel tops are not cheap. So for these guys, that was a major driver. And it also eliminated that processing step of the extra grinding process. So, and this is a good example of, because of the heat that is needed on this application, it's actually a silicone that they're using to structurally bond that top to the bracket. So not something you might traditionally consider a structural, but because of what they needed, it was the right product for them. And then I guess the real last one, and I put real life in quotes because I don't know when this might actually be a pertinent application for you, but in an effort to show kind of the impact resistance of adhesives versus tape versus mechanical fasteners, we actually put together aluminum panels. You can see one of them here. And right down the center here, there's two aluminum panels assembled together. In this case, this was actually screwed together. And we shot baseballs at the batting cage. And that was our impact test. And it's a fun example of a quote-unquote real life, showing how much more impact-resistant adhesives can be versus some of these traditional methods. So if you go to the website, hinklena.com/Loctite Structurals, you can see that there. So in summary on my end, why would you use adhesives? It's the cost savings. Improved strength and aesthetics and reduced labor are the drivers, but they all add up to in some way or somehow they're putting more money in your pocket, and that's the important thing. So that's the number one reason to go and use adhesives. We cover a little bit of joint design. You want to maximize tensile compression and shear and minimize cleavage and peel, and that's going to help you have a better joint design, which is going to be more conducive for adhesive to work. We covered some real-life examples, and then talking about why Loctite, us being the #1 adhesive company in the world, is really the main reason why you'd want to partner with us. We talked about equipment. Loctite offers a full line of equipment from large bulk dispensing systems down to manual, so we can provide a total solution, which is nice. You're not just going to get the adhesive thrown over the fence and you have to figure it out. We'd like to partner with you. Another thing, if after today you have questions about your applications, you can get one-on-one support at 1-800-LOCTITE. And the beautiful thing with this number is you're actually calling people that sit right outside my door that spend half their time in the lab working on customer parts and applications. So there's not speaking from a cheat sheet off of a binder. This is people who actually really know what they're talking about. And you can also go to the website, which I talked about. And on here, there's case histories, so more real-life examples to help build some confidence. Some of the videos I talked about, and then also the white paper, The Hidden Cost of Instant, which talks a lot about some of the detailed testing we've done and the background work that went into creating this presentation. If you are more of a reader, you can check out some of our design guides for bonding metals and plastics, and this will give you a great feel for shear strength of varying adhesives on different substrates. So this is a great tool to help get you in the right ballpark if you want to try something on your own, or you can always give us a call and we can help you out. So that's really all I had for today. Hopefully you've learned something, and I would love to answer any questions you may have at this time.
Thank you, Brian, and now we will open up the remaining time to questions. One of the first questions that has come in is, you mentioned tensile and peel forces. What about impact strength?
Yeah, it's a good question. We talked a little bit about the impact strength in that video. So, one thing you can do is go there to see in real life how it works. But the other thing is, when you're talking about these different adhesives, many of the latest innovations that have come out have been to improve impact strength. So epoxies tend to be very rigid. There's things you can do to improve that, but some of the latest innovations have been to improve impact strength of adhesives. And you can see it in real life on that video, or you can go to talk to some of our professionals, and we can tell you some of the things that we're doing to improve that property.
Okay, and we have another question here. What about parts that go through paint bake?
Okay, that's a good question. A lot of times with the final assemblies, they go through some type of paint process. If it's a wet paint, something under 250 degrees Fahrenheit, pretty much any of the adhesives we talked about today would work. If you have a part that's going through e-coat or a paint bake oven above 250, usually around like 400 to 450 Fahrenheit, what can actually happen, to the prior question, is the adhesive that's there might actually kind of improve in shear strength, which you'll see a lot of times, but the impact strength goes down dramatically. And there's some specific heat cure epoxies and some two-part acrylics that we've developed that kind of address that paint bake process, and there's not too much else out there from an adhesive standpoint that can survive that. So that's a good question.
Okay, and we have another one here. What about temperature? What happens if it gets really hot or really cold?
Okay. At really low temperatures, typically you're talking about a minus 40 glass transition temperature for some of these products. So if you're going below minus 40 F, which is the same Celsius, I guess. If you go below that, that's when you start to see a dramatic shift in the properties of the thermoset adhesive. So anything below that, you'd want to test and try and see at that temperature, because you've dramatically changed the properties of the product. For most of the other products, you're talking between 300 to 400 degrees Fahrenheit, and silicones maybe up to 600 degrees. So those are really your max and min temperatures where you want to play with adhesives. And as far as if you have a part that's seeing thermal shock or thermal cycling over different temperatures, that's something we can simulate in our lab to prove out if it's going to work. But again, the nice thing about using the adhesives is they're going to be able to absorb some of that contraction and expansion over time. So there's things you can do in adhesive selection to address that if you know what your part's going to see.
Okay. We have a few more minutes. If anyone else has some more questions to ask, feel free to write them down, and we'll be happy to ask them. In the meantime, as we wait for some of that, Brian, how would you say on average is maybe the number of different types of applications that can use adhesive versus mechanical means?
That's a good question, Leslie. I mean, if you look at applications, for the most part, if you're not exceeding that temperature range, there's a good chance adhesives will work. And the real question then becomes, is whatever cost savings you're going to get, is that going to offset the design time to an effort to change the design or to make it fit into your application? So if you're within those temperature limitations, and we didn't talk about it today, and a lot of these applications don't reference it, but they're, chemicals can do a number on adhesives too. So if you have some really, really aggressive chemicals, that can eliminate them right off the bat. But if you pass those first two tests, for most cases, I'd say maybe 80 to 90% of the time an adhesive can work. And one of the things that we found too is that there's a potential. In many cases, you can't completely eliminate mechanical fasteners, so you may need to use one or two rivets or spot welds to fasten the part. and the adhesive is what gives you the ultimate strength. So that's kind of how we would address that.
Yeah, I was kind of interested in your conversation about disassembling once you've used an adhesive. That's interesting that there are more ways to do that than maybe one might have originally thought.
Yeah. Actually, the trailer example, the bonded trailer, that's an elastomeric adhesive, and that's their number one concern, is because if someone hits that trailer, or you do something, you bump into it, and you want to replace a panel, it's not worth the cost of it to take a blowtorch to the whole thing and do it. So the product we chose is elastomeric, so you can actually cut it out with a piano wire, just like you could a car windshield when they repair it in the parking lot over your lunch break. So if you know it's something you need to do up front, you can make some choices to make that easy for you to do.
So it definitely sounds like you really need to know your application, and once you do, you can make some really good choices.
Exactly, and that's where, I probably didn't say this enough, but, one of the things that we like to do here is if we can be involved up front and help with the design and the selection in what you're doing, it's going to make everyone's lives a lot easier. We put out fires every day. If there's a problem, we are glad to solve it, but getting involved up front is a great way to make sure you minimize those and you're thinking about these things out front, because if there's a problem, we've probably bumped into it.
Can you get the question? Hang on one second. We've got somebody who's phoning in a question.
Sure.
And she's writing it down now, so it'll be here in just a second. It looks like it's a long question.
Uh-oh.
It might be an application question here for you.
That's all right.
Yeah.
He wants to know how using the urethane adhesive product on a large format vehicle, how will that work when it's originally equipped to use a rubber seal?
Okay, when you're on a large vehicle, how would you compare a urethane format adhesive versus...
Well, how will that work when the original equipment is made for a rubber adhesive?
And how would that work on original equipment that was made with for a rubber adhesive?
Okay, that's a good question. A lot of times the rubber-based products, and if I'm understanding it correctly, they're curing by some type of solvent or moisture flashing off. So that equipment is probably designed to keep, to not allow moisture to come out. Versus the urethanes, they're actually relying on moisture to get to the adhesive, which is allowing it to cure. So the benefit is they're probably both one-part systems. So, and a lot of times there's probably a lot of those parts that can be kept and used the same, but there might be certain fittings or things where you might need to tweak and change to make it work. So there's probably, not knowing the real specifics, there's probably parts of it that could be reused and maybe a few things you'd want to switch. And you definitely want to work to make sure you got the right flushing fluid so you get whatever's in there now out before you do the changeover. So that would probably be a good call for the 1-800-Loctite number. In our labs, they're consistently using one product and flushing it out and putting in a new one for a new test. So that would be a good call for them, where they could share more specifics about what the products are, and they could either help out or transition it to a local specialist.
Okay, I'm getting another one, and it's also being phoned in, so hang on.
Sure, no problem.
This will be the last one of the phoned-in ones, and so if anybody else on the in the webinar, if you do have other specific questions, Brian's email address is posted online, so you can go ahead and email your questions.
Yeah, I'm glad to answer them.
Okay, here's the next one.
Okay, what testing does Hinkle do to ensure the products are going to last for outdoor weather, and what do they recommend?
Okay, what kind of testing do you do to ensure that your adhesives will last in outdoor weather, and what products would you recommend for outdoor use?
That is an excellent question. You know, one of the great things about Hinkle, I'm here in our worldwide headquarters for the Loctite brand in Rocky Hill, Connecticut, and this facility has 400 people here, and one of the beautiful tools we have is an ISO accredited laboratory with almost any type of standard test method you can imagine. So we've got thermal cycling chambers, QUV to simulate sun, heat and humidity conditioning chambers, so we can simulate virtually anything that a customer could dream up and want to see and create the data to build confidence. So, you know, one way to do it is to tell us, hey, we believe or we have the specification that it has to meet, and we can actually do all the testing and prove the data, which is, you know, independently validated and real, to show how our products compare to an incumbent solution. So that's one way. And the other way to do it is to look at some of the existing applications. You know, I mean, we could do a lot of testing in the lab, but if there's one thing I've learned, there's nothing better than actually trying it and doing it. So, you know, in the case of a trailer manufacturer where the cost of failure might be low, maybe that means you make one and you drive it around yourself and you prove it out, you know, prove out the concept yourself. And in other cases, maybe you want to do a lot of that lab testing. Either way, we can help do that. And to the second part of that question that might speak to, you know, what type of adhesives would you use? Typically for outdoor applications, you'd want to go either with an acrylic solution. Two-part acrylics are used a lot in the marine industry. They're one of the solutions we've used at Thomas Bus. And so the acrylic chemistry is a great solution. And the other two, urethanes. If they're in direct sunlight, urethanes can degrade over time, the color and the properties. So if that's the case, maybe not the right choice. But if it's a bond, if you're bonding it in between two substrates, urethanes will also be able to. The major differentiator between those two products is they're more flexible. So over time, as parts heat and cool and move and resist moisture and things like that, that's what makes those two the best choice for outdoor type applications.
Okay. Thank you so much, Brian, for putting on this presentation about adhesives, and also thanks to Hinkle as well. We really appreciate this information. Good tutorial. Thank you to everyone who attended this webinar from Design World. This presentation will be emailed to you shortly, and it will also be available at www.designworldonline.com. Thanks again for everyone's attendance.